This spirograph sounds like this. And the reason why is something called polyrhythms. So the first thing we have to talk about is what even is a polyrhythm? Well, a polyrhythm is when two pulses line up with each other in one set of time, like one bar. If we had a bar of 4, 4, and we had the pulse going 1, 2, 3, 4, and we also wanted to have a pulse of 3 in that same amount of time, it would sound a little something like this. So, in that beat, you can hear 4 clearly, and 3. One more time. You've probably heard of these if you've ever listened to somebody like Jacob Collier or watched an Ava Lim video. They're pretty common, but they're a little bit hard to do. Maybe you can intuitively feel what a 3/4 polyrhythm sounds like. But what if I asked you, what is the relationship between the second triplet and the second quarter note in that polyrhythm? Well, if we just thought about 3/4, we wouldn't really know. That notation would look something like this. And yes, it does accurately notate what we were just hearing, but it doesn't give us exactly where those notes are in terms of each other. To do that, we must subdivide some of those notes. For the 3/4 example, we could make each quarter note into groups of triplets. Then we could tie together groups of 4 triplets to make exactly 3 notes over the 4 quarter notes we have. And that would look a little something like this. Even though this looks different, it sounds exactly the same. And now we're able to accurately tell where these notes are lying within the measure. For example, the second note of 3 lies exactly on the second triplet of the second quarter note. If we were to change the overall pulse to 3 and have a 4/3 polyrhythm, we would have to divide each quarter note into 4 16th notes. Then we could tie together groups of 3 16th notes to have exactly 4 beats over 3 quarter notes, and it would look something like this. Something you might notice when subdividing in 3/4 and 4/3 is that you need 12 subdivisions per bar to be able to accurately count out the beats. This is because that number has to be divisible by both pulses, which means 12 is divisible by 4 and 3. This number is called the smallest common multiple. If you wanted to make a 5/3 polyrhythm, you would need to find the smallest common multiple of 3 and 5, which is 15. That means you would have to divide one bar of 5/4 into 15 beats to be able to accurately count a 3/5 polyrhythm. And that would look a little something like this. We can also make polyrhythms with more than 2 pulses. For example, if we wanted a 2/5/3 polyrhythm, we would have to subdivide the bar into 30 subdivisions, which can be made by subdividing our overarching bar of 3/4 into 6 groups of 16th note quintuplets. As you add more pulses, you have to add more subdivisions, and obviously comes a greater level of difficulty. Jacob Collier is somebody who's mastered these polyrhythms, and he can do a 2/3/4/5/6 polyrhythm on just one hand.
So this is 2 against 3 against 4 against 5 against 6. Right, here we go. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 1, 2. Like that. It's just so silly, but there it is.
It's pretty crazy, huh? But if you haven't mastered those polyrhythms like Jacob Collier has, there's an app called Concentric to help you get practicing. Concentric will help you lay out polyrhythms in a visual way that will help you easily understand where each note is. So this is what Concentric looks like when you open the app. Each ring represents one pulse. So we already have a pulse of 4 here, and if we wanted to make a 3/4 polyrhythm, we could add a ring of 3. It would sound like this. And then we can change each pulse to have a different sound. Maybe we want this to be an instrument. And then we can even look into the rings and fine-tune them. So now we just put this halfway between 2 and 3, meaning that this is technically subdivided into 8 pulses. But this is still a 4/3 polyrhythm. We're just hitting different notes. Let's add some more. We can randomize them. And even randomize the notes. If we wanted to look at each ring separately, we could do this. And even mix each ring. So you can make a lot of cool things with this, a lot of cool beats and rhythms, and all of it's based off polyrhythms. But what if I want to spread these polyrhythms over more than one bar? Well, now we're talking about polymeters. Unlike a polyrhythm, polymeters share the same pulse. Because they share the same pulse, there's no subdivision involved. A 3/4 time over 4/4 time polymeter would just be accenting every third quarter note in 4/4 time, and it would look something like this. The groupings of 3 and 4 quarter notes are now phrases, and they aren't trying to smush into one time together, they just take more time for them to line back up on one. In this example, it takes 3 bars of 4/4 or 12 quarter notes for both phrases to line back up on beat 1. 12 beats for 3/4 and 4/4 time to get back to 1. Does that sound familiar? Let's try it out again, but with 3/4 and 5/4 time. It would look like this. Again, the number of beats needed for the two phrases to line back up on 1 is the smallest common multiple of the 2 meters. For 3 and 4, it took 12 beats, and for 3 and 5, it takes 15. We can demonstrate this in a different way by counting out the numbers 1 through 5 against the numbers 1 through 3. It takes 3 groups of 5 and 5 groups of 3, or 15 beats each, for the phrases to line back up at 1. But personally, I don't really like the way this looks. It looks very linear and unfinished, when we know this is a repeating pattern. Concentric lined this up in a nice circular way, so could we do the same thing here? What if we made the numbers 1 through 5 into a circle? This would represent 1 bar of 5/4 time. Then we know we would have to accent every third beat to represent 3/4 time. We can do this by counting out 1, 2, 3, next beat, 1, 2, 3, next beat, 1, 2, 3, next beat, until we get back to 1. Connect those dots and you get a shape that looks like this. We know that the circular representation is accurate by relating it back to the linear example. The second downbeat of 3 hits on the 4th beat of 5. The third downbeat of 3 hits on the 2nd beat of 5. The 4th downbeat of 3 hits on the 5th beat of 5, and so on. Let's try again with an 8/4-6/4 polymeter. Now our circle has 8 beats, and we're skipping to every 6th one. You can see that when we're skipping to every 6th beat, we aren't actually hitting every beat in 8. This is because 8/4 and 6/4 can be simplified down to 4/2 and 3/2. Making a circle of 4 and jumping to every third beat, we can see that we make the exact same shape. By writing out the linear example, we can see that both of them have 3 groups over 4 groups, meaning that they sound the same. With this example, we get an important piece of information. If you keep the ratio of the meters the same, they will sound the same. But what does any of this have to do with the picture of a spirograph? Well, when I was doing research, it turns out there's actually a lot of material on visualizing what rhythms look like. These include everything from Euclidean rhythms, Lissajous patterns, harmonic polyrhythms, and even nunchuck patterns. There is an astounding amount of information here, but one thing in particular caught my eye. Robert Inventor's website on what he calls epicycles, or what we know as spirographs. Spirographs are something that's always fascinated me. I love the shapes they make, and I love the math that goes behind it, but I've never really understood how it works. So I dug out the old spirograph kit and started getting to work. As I was creating patterns, I realized they were looking really similar to the circular polymeter patterns that I was making earlier. And I realized if the ratio could go down, it could also go up. I started with a 3/4 over 4/4 polymeter. If you multiply those up by 24, you get 72/96 and 96 over 96. And these are number of teeth on the spirograph set that I had. So I got the 96 teeth ring and the 72 teeth gear and made a pattern, which ended up looking like this. If we dig a little deeper and label each petal 1 through 4, we can tell that the spirograph is actually skipping to every third beat, just as if we were drawing a circular polymeter diagram like before. Let's take a closer look. So remember, this outer gear is exactly 24 times 4, which means that one time around the outer gear is 1 bar of 4/4. The inner gear represents 1 bar of 3/4. We start with the two gears lined up at 1/1, represented by the 2 hearts. Remember that the outer gear represents 4/4 and the inner gear represents 3/4. As we start moving the gear, every time we come back and hit the top, the red heart, that marks 1 bar of 4/4. If we do it again, there's another bar of 4/4, and finally 3 bars of 4/4. That gets us back to 1/1. Now let's count bars of 3/4. A bar of 3/4 is marked by every time the inner gear makes 1 full rotation, or when the pink heart comes back to the outside. That would be the first bar of 3/4, the second bar of 3/4, the third bar of 3/4, and at the fourth bar of 3/4, we're back at 1/1. If we divide the outer gear into 4 equal sections and the inner gear into 3 sections, we can even more clearly see how this is a representation of the circular polymeter diagrams we were doing earlier. Now let's try with an 8/4-5/4 polymeter. Multiply those numbers to numbers of teeth we have in the spirograph, and you get 96 and 60. Just as you would expect, the outer ring is divided into 8 beats, and the inner ring is skipping to every 5th beat. This polymeter would sound like this. So now finally, we can get back to this spirograph. This spirograph was made by using the 96-tooth outer gear and the 52-tooth inner gear, which can simplify down to being a 24/4 and a 13/4 polymeter, which would sound like this. And that's how we know what spirographs sound like. Thank you so much for watching. This has been my final project for Music 457 at University of Washington under Ted Poor. I had a lot of fun in this class, and I learned so much about polyrhythms and polymeters, as I hope you can tell. This project was something that took me very far away from music, but really it gave me perspective on what the heart of music really is. It's ratios and it's math and it's art. And I had a fantastic time doing it. I hope you learned something. Thank you so much. Goodbye.